Thanks, Professor, for your nice introduction. This is a joint work with Abel Bustos from Universidade Sérgio Arboleda from Bogotá, from Colombia, and with Wanderson Lambert from Federal University of Alfenas, Brazil. This is the summary of my talk. First, I'll discuss quite briefly the stiff relaxation system that we are interested in. Then I will move to the computational modeling, take advantage of this previous analysis and the modeling of the balance law equations. Then I will compare some numerical calculations and with our formal calculation. And finally, I will conclude with some remarks. So let me start by saying many thanks to the organizers, to the invitation to be here. It's a big pleasure to be here. And of course, the Brazilian funding agents to enable the work. And so in this study, we are interested in this late time behavior, the asymptotic behavior of solutions linked to the stiff system of equations with applications in porous media, in particular with oil recoveries and remediation process in groundwater contamination process, as in this topic of this conference in porous media. And specifically, in the absence of gravitational effects, such flow can be modeled by a system of n+1 equations, as it reads here. Here, the epsilon is a time relaxation parameter. Our interest is to study this system when this guy here goes to 0, and the variable here are these nice looking capital V here, the thermodynamic equations variables, and little u is the Darcy velocity. And in this formulation, G, capital G and capital F stand for the vector value functions, as read here, where the product of the velocity of Darcy law and the capital Fi is the flux of the conservative quantity. So in this model, G is the conservative quantity here, and this derivative with respect to time is the corresponding accumulation term. So by construction, as we can see here, U appears only in this partial derivative, so G is not invertible. This is quite simple observation and helped us a lot in the numerical modeling to its numerical solution. And so in the right-hand side, we have the source term, and the first n component represents the mass transfer of the phases, and the last equation represents the energy transfer due to the phase change. I would like to mention that a general formalism for this system when the source term is equal to 0 was done by Wanderson Lambert under the guidance of Professor Hans Bruining and Professor Marchesin here at IMPA. And our interest here is to case a different situation to account this relaxation process under a thermodynamic equilibrium. So if G is precisely the thermodynamical vector functions, variables, and U is the constant in equal to 1, now extensive literature is available for such system, but with lack of general theory for existence, stability, unixes, also numerics, as the relaxation time goes to 0. Sorry if I forgot some of key reference here, but this is that to show that this area is quite activity and important from theory, from numerics, and from applications. And concerning the thermal model problem, I'm not going into details in the modeling here, but although the well-known instantaneous equilibrium hypothesis introduced by Helmrich in 81, in which gave rise to a frontal advance in theory for multi-component and multi-phase displacement in porous media in petroleum science and engineering, there are a number of recent works that assume the same local equilibrium as we can find here. But these authors were not able to explain discrepancy between numerics, the theory, and the laboratory experiments. And in this regard, at least in our opinion, a tantalizing speculation is that the relaxation may be the ingredient for comprehension to the correct physical modeling for such equations. This is what I'm trying to figure out. So, to be quite simple here, we consider a 4x4 example in which the relaxation solution and the equilibrium solution differ in the physical space, but the same solution agree in the phase space. Also, we were also able to study, at least qualitatively, how is the behavior of the solution in this limited process, at least from a qualitative point of view. So, as I mentioned, I will not go into details, but we are closely related to the work of Professor Bruining and Marchesin, in which describe this full set of model that is quite hard to understand everything, but the unknown here are the thermodynamic variables, the temperature, the gas saturation, the steam gas composition, phi Gn, and the Darcy velocity. The assumption is the porous medium is fully saturated, so the saturation of water and gas add up to 1, and it be possible to write as a function of water or gas whenever possible. This little k is the mass transfer. So in this modeling, it's possible to identify 3 primary variables: the gas saturation, the temperature, and the steam gas composition. And U appears only in the spatial derivative here, 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 and here. And it's possible actually write the Darcy velocity as a function of these 3 primary variables. And we use this fact, take advantage of this modeling in order to write a stable numerical scheme. So this system, this system too has 3 positive eigenvalues. We also take advantage of this information in the numerics. And the last equations, due to the modeling, we found that it's possible to write the conservation of energy in terms of the entropies. And these, the entropies vary up to 3 orders of magnitude with respect to the other 3 equations with the 3 primary variables. And then these also guide us in a way to conveniently rewrite the equations to their numerical solution. So we take advantage of this very hard model to make the computations easier. So, and the question here is, what's the link between the asymptotic solution of model 2 and its limit solution as this scaling parameter go to 0 and time go to infinity in the thermodynamic or natural equilibrium. This is what we are trying to do here. So the system 3 can be written in compact form like this. Let me describe some issues that is relevant in this work. So when we take the source term equals 0, it's possible to define what we call the stratified equilibrium variety. And this stratified variety is formed by m different sheets. And in each sheet, it's possible, at least formally, rewrite system 3 as a system of hyperbolic conservation laws with less unknowns and less equations. And in a certain point of view, we can take advantage of this reduction in order to solve this from analytical point of view and from numerical point of view. And it's possible to write equation 3 as this equivalent equilibrium system, in which capital G tilde and F tilde is written in terms of these original functions of the original system. So the idea is to compare the numerical solution directly applied to this equation 3 against the Riemann solutions for this equation that is precisely this one projected in this stratified variety. This is the idea. So, some technical details that I'll try to concentrate on the important issues. In this situation, in the stratified equilibrium variety, we have 3 physical situations: the gaseous phase, the liquid phase, and the gaseous plus liquid phase. Here, we will concentrate on the third one that we found to be richer than the previous two. And the thermodynamics unknowns here are the temperature and the steam gas composition. And these source terms represent, as we expect from the modeling, the physical tendency to the physical equilibrium. And as announced, we are following the formalism introduced by Professor Bruining and Marchesin to model the source term that is quite hard to handle. So this is the picture. We have the sheet here, the stratified variety. So here we have a 2-phase situation and a single-phase gaseous situation here and a single-phase water situation here. And from theory and numerics perspective, we have 2 main interests in here. The first one is to improve our comprehension from the theoretical point of view. And the second one is to develop a numerical approach in which can handle the coupling between the hyperbolic conservation law and the balance law. It's possible to have distinct regions with distinct flow configurations. That is modeling by a system of balance laws, and this modeling by a hyperbolic system of balance laws. And we'd like to describe a numerical scheme that can handle these 2 kinds of flow situations without any kind of numerical trick, and not to be intrusive in the computational modeling. So this is the equation in the equilibrium variety here, as announced before. And let me describe quite briefly how we proceeded to the analytical solution. So first, we compute the eigenvalues and the waves to the complete system disregarding the source term as announced. We solve the Riemann problem for the projection of the Riemann data in the variety. And here we have some new things here. We study the behavior of each wave shock rarefaction in the solution and its interaction with the source term. And next, we identify if the source term is dissipative. That is quite important. And we study the existence of traveling waves profile supported by the source term. So with this in mind, we now move to compare the results with the numerical solution. So let me describe the big picture. Taking advantage of the modeling, we were able to identify 2 subsystems, one that better model the thermodynamic variables, in this case the temperature, the gas saturation, and the steam gas in blue, and another subsystem that model the Darcy velocity. the situation here is in the spirit when we solve a second order elliptic equation. It is a PDE of second order for the pressure, and take advantage of the Darcy velocity and the relation to the pressure. We can write this second order as a two system of first order with less stringent requirements to be more stable or more conditioning to its numerical solution. So here's the idea. So we solve, here now we have an evolution equation. So this framework is for each time step. So for each time step, we first solve these subsystem of equations and take advantage of this information of the temperature, the gas, and the steam. We can solve the Darcy velocity from this last equation. And if needed, we can use some kind of Picard iteration to improve the accuracy of the solution for each time step. In our case here, this is not needed, but it's possible to take advantage of this formalism for its numerical solution. So let me describe quite briefly each part. The blue part, let me show the balance law. The issue here is to develop a well-balanced scheme in which, in the discrete level, accounts the delicate balance between the source term and the hyperbolic flux. Our experience in this scheme suggests that do not use a splitting approach, since you can decouple the equations and lose the information of the overall equation. So the crucial issue here is how to compute V from G, as we need to invert. So to see this, we define two computational grids in an original grid, in a staggered grid, define as usual an average. Here, as you can see, is a general formulation, so you can use the scheme of your choice. Our scheme is developed by taking some quite appropriate integration of this quantity and this quantity here. I will not go into details here, but I can give you the reference if you wish. And the idea is when you solve the equations from time step n to time step n plus 1, you go to the original grid to the staggered grid. And in staggered grid, you can solve this nonlinear equation to recover the quantity V. And then this means that you can use Newton's method easily. And after this step, you can project the solution from the staggered grid to the original grid. And again, the modeling and analysis is crucial here. So the Darcy velocity, when necessary, the Darcy velocity is none from the inflow boundary, and easily you can use some kind of finite difference scheme or finite volume conservative scheme by upwinding, since in this case we have the positiveness of the eigenvalues. But the situation can be difficult if you take the gravity in the situation, but this formula can be used. You have the counter flow, so you need to take care on the boundaries in order to account the interaction of the wave that goes back. But it's possible to do this. So after some simple calculation, you can calculate the velocity u explicitly as follow here. So this is a sequential approach in a mixed formulation. And for each part, as I mentioned, you can use the method of your choice. There is no reason to use our scheme. So to compare and to finish the talk, we solve the equation with the full model. So we have here this is Riemann data. And under the stratified variety, so you can see here the same data. Of course, you have a less one equation. And on the right, in the phase space, we have the solution for temperature and the gas saturation. So this is the solution in blue. On the left, we have the blue solution here, superimposed with a sequence of decreasing scaling factors. As I mentioned, we used a very large set of these scale factor, but here we are just showing as a representative set to show this behavior. Here in the steam gas composition, we can see here how things comes integrate. As we decrease this scale factor, we see here how the structure of the solution changes a lot as we decrease. And in the limit, it seems that we have this limit here that is quite different from the solution in the equilibrium. So we have different situations in the limit process, and in the limit is quite different. So this is the same for the temperature, for the gas saturation, as we can see here, and to the density velocity that is not constant, as mentioned before. Here is the illustration of the analytical solution. We were able to analyze this in details and to understand with more details what happens here. So we have these quite intricate solutions. It's possible to identify each part, but the point here is the numerical solution agree with the analytical solution. So we are quite confident that our computations are correct, although we do not have rigorous numerical analysis to this numerical procedure. So to finish, we were able to give a simple 4x4 example in which the relaxation solution and the equilibrium solution differ in the physical space, but in a good agreement in the phase space, and this enables us to study the asymptotic late time behavior of the solution. We use some new formalism to the interaction of the solution in the stratified variety. The numerical procedure can be written in a mixed sequential approach, in a predator-corrector step, avoiding Riemann solutions and the operator split procedure. That is not advisable for this set of equations. And we also able to use this same framework for hysteresis and for all equations with frictions. For this case of hysteresis, we have gravity and we have this kind of Coutinho flow that can be used by this numerical scheme. As a work in progress, I would like to put the gravity in the picture to see what happens, a more challenging situations. Some suggestion, advice is welcome here for the audience. And keep in mind the words of Professor Bruining, that allows statistics and relative permeability to add modeling of this kind of set of equation that for sure is quite hard. And I'll stop here. Thank you for your attention.